Hi guys, Audrey here. So we remember L'Hopital's rule is a rule that tells us that if we plug in and we get the indeterminate form of either 0 over 0 or infinity over infinity, then when we're doing the limit to deal with that indeterminate form, to find out what value it's hiding, we can say that that equals to the limit as x approaches c of f prime of x over g prime of x. In other words, we can do the derivative of the top divided by the derivative of the bottom. Now, we also saw that sometimes we might have to use L'Hopital's rule more than one time. So we can use L'Hopital's rule as many times as we need to. We just need to remember that before using it again, we always want to start off by simplifying. So today we're just going to do one example here to kind of remind ourselves of what it is and how to justify our use rather of the rule. So here I have the limit as x goes to infinity of arctan of 2x divided by minus pi over 2 divided by sine of 1 over x. So clearly the first thing I need to do anytime I'm evaluating a limit is plug in. And so here, I'm going to have this arctan of infinity. So we need to figure out what is happening with arctan as what's inside gets closer to infinity. And a good way to think about that is to remember the graph of arctan x. So this is actually a graph that's going to be quite important for you this semester. So you should definitely remember this graph, be comfortable with it. Arctan, we know, has a horizontal asymptote up here at pi over 2, and it has another horizontal asymptote down here at negative pi over 2. And then it ends up looking like that. So we can see here that as my arctan, as the values inside are going to infinity, my x values are getting bigger and bigger and bigger. My y values are approaching that asymptote, and this is going to pi over 2. Whereas if we were to look at arctan of negative infinity, we're saying what happens as my x values get infinitely small, we can see that it's going to that asymptote there of negative pi over 2. Okay. So in this case, we have that arctan of 2x. That's just our arctan of going to positive infinity. So when we plug in up here, we end up with pi over 2 minus pi over 2. Now, what about sine of 1 over x? So here we're looking at sine, and we're letting that x value get closer and closer to infinity. So it's like we're looking at sine of 1 over infinity. Now we remember as the bottom gets really, really, really big, the whole thing's going to be getting really, really, really small. So this is like saying sine of 0, which we know to be 0. So we can see here that plugging in does actually give us 0 over 0, which is awesome because that is indeed one of the forms for which we are allowed to use L'Hopital's rule. So we will say then that this is equal, I'm going to have my little h because I'm going to be applying L'Hopital's rule. So the derivative of arctangent of 2x is going to be 1 over 1 plus 2x squared, but then we have to multiply by the derivative of 2x, which just gives us a 2. So here I'll go do that on the side so that we can see the derivative of arctan of x over a, we know is equal to 1 over x squared plus a squared. So here what I have, I can think of this as 2x over 1, so that my a here is 1. So then this is 1 over 2x squared plus 1 squared times the derivative of 2x, which gives me 2 over 4x squared plus 1. So I'm actually going to go replace that up here, that 2x squared that we have like that, with a 4x squared. Now, the derivative of pi over 2 is just 0, so we're good there. divided by the derivative of sine of 1 over x. Well, the derivative of sine is cosine, but then we need to remember to do our chain rule, so we're pulling out the derivative of 1 over x. So that's like negative 1 over x squared. So here we can go down and do this as well. The derivative of sine of 1 over x is cosine of 1 over x times the derivative of 1 over x. So that's cosine of 1 over x times negative 1 over x squared. Now, hopefully that's a derivative that you are comfortable with from all of the integration we've been doing. But if not, remember that this is like x to the negative 1. So it's negative x to the negative 2. And that's where that negative 1 over x squared comes from. Now, we have been told that before we just immediately apply L'Hopital's rule again, oftentimes before we even plug in again, we should always simplify first. We want to get into our simplest form so it's easy to plug in. And so if possible, we can get rid of any possible reuse of L'Hopital's rule. So here when I simplify, I'm going to say that this is the limit as x approaches infinity of my numerator. So I'm just separating my numerator out. Then times 1 over my denominator. And so then I can see, so here we're simplifying, so I'm going to write that. So I can see here that this is actually equal to the limit as x approaches infinity. This negative 1 over x squared right there, I can actually bring it up to the numerator. It's the denominator of my denominator. So this becomes negative 2x squared over 1 plus 4x squared times 1 over cosine of 1 over x. All right, so if I were to try to plug in here, what I would see is that this thing right here is giving me an infinity over infinity, and that this thing right here is giving me a 1 over cosine 0, a 1 over 1. So that cosine of 1 over infinity gives me a cosine 0. So that's just a 1 over 1. So like this part right here is an indeterminate form. But this part right here, I already have the answer to. Like it's just 1. So this is like easily done by plugging in. So what I'm going to do is I'm going to remember my limit rules from last semester and separate this into 2 different limits that are more easily manageable. So in other words, I can actually distribute limits inside of multiplication. So I'm going to have a limit of negative 2x squared divided by 1 plus 4x squared times the limit as x approaches infinity of 1 over cosine of 1 over x. So here what I just did is separated this into 2 different limits that are more easily manageable. Okay, so all of this is like side work. So I'm just going to put it in a bubble. And then we'll go down here for the continuation of the limit. I'm just going to rewrite it so that we're clear where we are. We have the limit as x goes to infinity of that negative 2x squared over 1 plus 4x squared times the limit as x goes to infinity of 1 over cosine of 1 over x, where we separated that into 2 things that were more easily manageable. And then this part right here, we said is just 1, because this is like 1 over cosine of 1 over infinity, which is like 1 over cosine of 0, which is 1 over 1, which equals to 1. Now, this other part, though, I'm going to call smiley face, and we're going to go do it on the side. So we actually have two different ways that we can approach this. And I'm going to do L'Hopital's rule, but then show you the way that's going to maybe make your life a little bit easier when we move forward with doing limits. So here we could say that the limit as x goes to infinity of negative 2x squared over 1 plus 4x squared. Plugging in here, it gives me infinity over infinity, or rather negative infinity over infinity. The signs do not matter for infinity over infinity, which means that I'm allowed to apply L'Hopital's rule. So I'm going to do that. So then we'll get that this is equal to the limit as x goes to infinity of negative 4x over 8x. Those x's cancel out, and this gives me negative 4 over 8, which gives me negative 1/2. So there I was able to finish this with just one more application of L'Hopital's rule. I want to point out that had I not separated those limits, in the denominator, I would have had a product rule because I would have had 1 plus 4x squared times cosine of 1 over x. And that product rule would have gotten gross, and it would have been a much more challenging problem. By separating these, I turned it into two really manageable things. Okay, so that said, another way that I could have done this down here, so we can say, or the limit as x approaches infinity of negative 2x squared over 1 plus 4x squared. What I can do is when approaching infinity, you can just take the big stuff. You can just take the biggest terms from top and bottom. And we'll be referring to this from now on as taking the big stuff. So the reason that we can do this is when I look at this, my denominator, the big thing in the numerator is negative 2x squared. So that's like the thing that has the highest power. When I look at the denominator, I have 1 plus 4x squared. My thing with the highest power here is 4x squared. So when I think about this in terms of infinity, 4x squared is really big. That's like 4 times infinity times infinity. It's like extra big. 1 comparatively is minuscule. When we think about this in terms of infinity, that 1 is literally next to nothing, right? It really does not change anything in terms of the denominator because that 4x squared is infinitely bigger. So what that means is actually I can just ignore it. The limit as x goes to infinity of negative 2x squared, and I'm just going to ignore that 1. I'm taking my big stuff, and now I can cross those out and get that this is negative 2 over 4, which is negative 1 over 2. So then we can go back up here and see that my final answer, we got negative 1/2 for that first thing, 1 for the second thing, and my final answer is negative 1/2. Okay, so I want to just briefly go back to this idea of taking the big stuff, just so that we make sure that we understand it. So take the big stuff. Let's say that I were to have the limit as x goes to infinity of 2x squared plus 9x plus 4 over x plus 2 squared. Okay, so here, this is also going to be a case of where we're going to infinity. We're going to infinity. We have just like rational functions. So I have like a 2x squared plus 9x plus 4, just a simple polynomial and a simple polynomial on the bottom. In terms of infinity, that 4 is infinitely smaller than the rest. That 9x is, even though it's infinity, it's infinitely smaller than 2x squared. So the only thing I need to do here is take that 2x squared from the top. On the bottom as well, I can look at this x plus 2 squared and be like, well, what would my biggest thing be? If I were to expand, I would take the x and the power. This would just give me x squared. So then I would have the limit as x approaches infinity of 2x squared over x squared, which is just equal to 2 after we cross out those x squareds. Now, if you really want to see, like, go more in depth as to why this works, maybe you'll remember what you did last semester and say that this is the limit as x approaches infinity, 2x squared plus 9x plus 4 over x plus 2 squared. I'm going to multiply both the numerator and the denominator by 1 over x squared. So then I will get the limit as x approaches infinity, 2 plus 9 over x plus 4 over x squared over, to do this, just so that we can really see, I'm going to expand this. So then I'll have this is over 1 plus 4x over x squared, so that's 4 over x, plus 4 over x squared. And we know that a constant divided by infinity is going to 0. So all of this stuff right here is going to 0 because it was infinitely smaller than the rest. So all we have left is 2 over 1, and we still get that same 2. So when we have rational functions like this, we can just take the big stuff. Everything else is infinitely smaller. Okay, so that is it for this video. Next, we're going to look at how we can use L'Hopital's rule on all of those other indeterminate forms that we saw.